In Chem Olympiad, we learned that carbons are chiral when they have 4 different substituents. So now you might ask yourself whether this applies for other elements and whether lone pairs count as a substituent. So we have 2 nitrogen compounds which have a lone pair and are bonded to 3 different substituents. And you might think that these 2 are enantiomers because they have a mirror image, but they are not superimposable. However, this is not the case because nitrogen has a very low inversion barrier. So essentially, these 2 compounds invert and they convert between these 2 states very quickly. So for example, ammonia, which is NH3, they invert 30 billion times per second between these 2 states. These R groups can mean anything. They can mean a hydrogen, a carbon, or anything else. Because it inverts 30 billion times per second, so it's impossible to isolate one of the enantiomers at room temperature. The mechanism of this is like an umbrella flipping inside out during a very heavy storm. So the lone pair that is in the sp3 hybridized orbital of the ammonia enters a vacant p orbital, and then it inverts. So it essentially pushes the other 3 groups from here to this side, and it enters another sp3 hybridized orbital. Okay, so these 2 are not enantiomers. However, when nitrogen forms quaternary ammonium salts, such as these ones, they are bonded to 4 different substituents, and they do not have they do not have lone pairs to invert. So like essentially these are actually enantiomers because there's no lone pair to change from one to the other. So as you can see, these 2 are enantiomers because it's mirror image and you can't superimpose them. So let's move on to the next set. Since now you're done with nitrogen, you might move on to like phosphorus, which is directly below nitrogen. However, phosphorus can form, these things are called phosphines. They are bonded to 3 different substituents and 1 lone pair, and they are enantiomers because they cannot invert and convert between these 2 states at room temperature. The conversion happens so slowly that you can isolate one of the enantiomers at room temperature. So these 2 are enantiomers, and the phosphorus is chiral. So this is essentially the answer to question 10a of the problem set 3. The phosphorus is chiral, so the whole molecule is chiral. Okay, now let's move on to sulfur, which is directly beside phosphorus. Similarly, sulfur, these are called sulfonium salts. They are bonded to 3 different R groups and 1 lone pair, and the sulfur is positively charged, in case you didn't know. And they also cannot convert between these 2 states because of the high inversion barrier, so it's very slow to convert. So you can isolate one of them at room temperature. So these are enantiomers, and you can't superimpose them. They are mirror images, but you can't superimpose them. Okay, we move on to this also applies for sulfoxides, which are sulfur double bonded to an oxygen and bonded to other substituents. So like this. Yeah. Unfortunately, I don't have a sulfur with like 4 different with 5 holes, sorry. So these 2 are mirror images, but they are not superimposable, and they cannot invert between each other. So they are enantiomers. Okay, that's about it.